Hello and welcome to the latest webinar by BitGardener. My name is John Kowalski. I'm part of the marketing team here. I'd like to welcome you. Today we have Ms. Ray Roby. She's the business line manager for automotive, speaking on color systems and the benefits of Delta E combined for auto-like finishes. Bit of housekeeping, we are recording this, so immediately following, you'll receive an automated email with the link. Feel free to pass that around, share it with colleagues, look at it down the road. Also, if we have some time available at the end of the presentation, we'd love to answer your questions. If you do have questions, please log them in the chat box located in the bottom right-hand corner of your screen, and time permitting, we'll get to them. If we do run out of time, we'll follow up directly with you to make sure your questions are answered. So with that, Ray, you ready to kick it off here?
Yes, I am. Good afternoon, everyone. John was saying, we're going to be talking about color systems and the benefit of the Delta E combined for auto-like finishes. So first, we're going to give you some information about CIELAB color space, and this was the original color space that was used for color systems in the beginning. And then the thing that is new or newer for this presentation is weighted color difference methods. And this is just for solid colors right now, but there's a lot of benefits to them. So whenever we talk about color, we have three basic building blocks. We have the illuminate. In this case, it's D65. We also have the sample. This is a blue sample. And then we have what we call is the observer. And the observer is important because there's two different observers. There's a 10-degree observer and a 2-degree observer. And if you use a different observer, you're going to get a different answer from the instrument. So initially, we communicated color in XYZ. XYZ coordinates are a little bit complicated. It's difficult to communicate color with XYZ coordinates. Also, the color space is not homogeneous, so different areas will have different sizes of ellipse. And then this is based off of additive, not subtractive color. And this also causes an issue because when we do things in with pigments and things, they are subtractive, not additive. So here you can see, depending on where we are in color space, our ellipses are different sizes. And the smaller ellipses in the bottom left-hand corner are more the violet shades. Those we have more sensitivity to color shifts in that area. And then the greens, where you see the big ellipses at the top, we're less sensitive to color change in those areas. So instead of communicating XYZ, CIELAB changed it to LAB or LCH, depending on if you have a chromatic or non-chromatic color. And here's an example of a tan that has an L of 62.51, an A of 3.31, and a B of 2.23. So the A value, if you look at the plot on the screen, positive A would be red, negative A would be green. And then for the B value, positive B would be yellow, and negative B would be blue. So for this example, you're getting like a tan color because you're positive red and you have some yellow. So that's giving you the tan color. So every color can be designated with coordinates in color space, and that would be the absolute values. So this is for a non-chromatic color. And you also have your L value, which 0 would be a perfect black, and L of 100 would be a perfect white. And then for the LCH coordinates, we have an orange color with an L value of 58, which is pretty much in the middle, a C value or chroma of 47.32, and a hue angle of 38. So the 0 angle for hue is that red axis where it says positive A in red. And then when you go counterclockwise, you're going from 0 to 360. So the different areas have different coordinates, and that's how you figure out what your hue is. So for chroma, you're actually coming away from the center point. So the higher the number, the more chromatic you're becoming. And then the hue value is actually the shift of the color itself. So if I go more to like counterclockwise from that C line, the chroma line coming out, I'm becoming more yellow. So I'm changing my color, not just the intensity of the color, which is the chroma. So hopefully that makes sense, because this is a question we get asked a lot. So basically, the system works kind of like the Munsell color system. So when you are closer to the center point of color space, you're going to have smaller tolerances than when you get out farther away and you're more chromatic. You'll have bigger tolerance. So we don't always talk about color in terms of absolute, because that would get a little complicated. So what we want to do is we want to do the deltas from our sample to our standard. So in this case, you have a delta L, we have a delta A and a delta B, and then there's a one number that we can use called delta E star, which is a total color value number, and that's just the square root of the sum of the squares of the other deltas. So in this example, if I look at the standard and then I look at sample 1, I have a delta E of 1. So in the industry, normally anything under a delta E of 1 would be considered okay, and anything with a delta E over 1 would be considered not okay. But in this example, on sample 2, all of my color variation is coming from my A value, so my red-green value, and it's all positive, so it's all positive A. So if I look at sample 1 and sample 2 versus the standard, you see that even though I'm getting a delta E of 1, my sample is quite different from my standard and would be unacceptable visually. So for CIELAB, there's always a definition for chromatic and non-chromatic for every color equation. And for CIELAB, anything under 10 for C is considered non-chromatic, and anything over 10 is considered chromatic. And these are all set up in, well, this one not specifically, but for the weighted color systems, those are already generated for you by the equation themselves in our Smart Chart software. So if I look at a non-chromatic color and I use the CIELAB Tolerancing, which is a box, the outside box, there are all the white dots are considered acceptable products, and the dots with the red X through are considered unacceptable products. So if I use CIELAB Tolerancing or LAB Tolerancing for this one, I will only have a few samples that technically should be rejected that are being accepted in this color space. Now, if I go to a chromatic color, if I make the box the same size to fit inside my visually accepted range, I'm going to reject a lot of parts that are visually acceptable. So this is something that's a problem, because we don't want to reject acceptable parts, because that costs us money. But if I use CIELAB Tolerancing, LAB Tolerancing, and I make the box bigger to include all of the parts that are visually acceptable, now I'm including a bunch of parts that should be rejected, which is also not what we want. So if we use chroma and hue instead of A and B, now we're getting this kind of pie-shaped box, I guess. And you're going to use chroma and hue, and now there's only a few rejected parts that are inside the box tolerancing. So this is why the C and H for chromatic colors is very important. And it also is better to use A and B for non-chromatic colors because that matches what we see visually. So this is an example of the CIELAB color space, and every area in this section is a different color, and all of these colors have the same size circle. So remember when we said that when you look at colors visually, they're not homogeneous. So in different locations of color space, you're not going to have a circle. You're going to have maybe an ellipse or some different shape. So this is why this equation, you basically have to take all your values and you would have to adjust them by what you see visually on your parts, because this is not going to adjust for you for different colors in different areas of color space. So it kind of makes it complicated when you're setting up for new colors. So if we look at the CIELAB color space, remember I told you that depending on where you are in color space, your ellipse is going to be different. So close to the center where I'm very like non-chromatic colors, everything looks more like a circle. And the farther away I get from the center point, I'm getting more of an ellipse. And then in the green area, like I talked about in the beginning, you are having wider tolerancing. So that center dot, hopefully you can see it, is say your master, and then all the samples that fall within that ellipse are going to be visually acceptable. So if I look in the red range, if I change my hue on a red, because remember, the hue goes around from the main red line all the way around counterclockwise. That's my hue changing. And if I come out from the center, I'm changing my chroma and I'm increasing my chroma. So a hue shift on a red, I'm going to pick up very quickly. If I have a hue shift on a green, it's not going to bother me as much. So this is why just setting the same color tolerancing for every specific or every color is not going to give you good information. There's going to be a lot of colors that you're going to reject when you should accept them based off of the numerics, or vice versa, depending on how you set them up. So that's very important to remember. And depending on your lightness, darkness, that's also going to give you differences in the shape of the ellipse, or in this case, when you're closer to the center point, the circle. So these are just things that you need to remember. So the darker I get, the less tolerant I am on changes in my color itself. And the lighter I get, the less that bothers me when I change in color position. So my circle or my ellipse is going to be bigger. So weighted color systems, there's a few that we use. Delta E CMC, this one was from 1984, and it was based on high chroma textile samples. So it's not a bad equation, but since it's based on textiles, it's normally just looking at the chroma and the hue, not necessarily lightness, darkness. And then Delta E94 was a revision of this Delta E CMC, and there was some more sample sets that they used with this. And they also used high gloss and chromatic solids for this one. And then Delta E9 or 2000 was published in 2001. And this one is also based on the same sample sets as Delta E94 and then some additional sample sets. So there's some more information that you get from depending on which equation that you use. So when we talk about weighted color systems, you're basically taking the delta L star, delta C star, delta H star, and you're dividing it by a scaling factor. So sometimes people will set up their own scaling factors because they have history of a color, or you could use weighted color tolerancing that will give you the scaling factor automatically based on where you are in color space. But the point of this is that you always, no matter what color it is, because you're using a weighted color system, you're going to use a tolerance of, if it's over 1, it's out of tolerance. So instead of thinking about it as like a color system, it's more like the percentage that you're out of your tolerance. So if I'm at 1, that means I'm at 100% of my tolerance. If I'm at 1.2, I'm out of my tolerance by 20%. And this is something that people need to remember when they're looking at weighted color systems, because if you think you're looking at the CIELAB number, then if you adjust something, it could be completely different than what you're thinking. So if, say, I'm at 1 on the CIELAB, I could be at 0.5 with a weighted color system. So those numbers are completely different. Just something you need to remember when you're looking at your data. And this is also why we recommend digital standards, because then you can control what people are using for the equations and what their scaling factors are set to be. And then you know everyone's using the exact same information to get the final output number. So this is very important. So Delta CMC, it was based on, like I said, visual evaluation of textile samples. And it was based on the following standards: British Standard BS6923, and the American Test Method 173, and also the ISO standard. Again, this is not rectangular like CIELAB was. It's going to be based on elliptical tolerancing. And it corrects for chroma and hue and lightness, and it's dependent on perception. So this equation, for some colors, especially non-chromatic colors, and some of the chromatic colors, works pretty good. But there's some limitations to this standard. And this is the equation that you're looking at. So in this case, the L times the SL is your scaling factor, and your little c times your SC is your scaling factor for your chromatic, and then your SH is for your hue variation and the calculations you can see at the bottom. It's just important that you know they're calculated, and that you can also modify the small L and the C in any software, because those are the two that we call application factors, and they can be modified. In the industry, it's normally 2-to-1 for the L and the C, and that's pretty much all that you need to know about that equation. And the L and the C is basically giving you the size of this ellipse. So the L is going to give you the height, basically, and the C is going to give you like the radius in the center part. So this is why you get an ellipse and not just a circle. So the ratio here, 1-to-1 gives you a shorter ellipse, and a 2-to-1 ratio gives you double that for your L value on the L axis. So 2-to-1 is what we normally do in the industry, but just so you can see how changing that number changes your elliptical shape. So again, it's really important that if you're submitting to an OEM, or if you have a supplier submitting to you, that you know exactly the ratio they're using, or you're going to get two different answers for what's pass and what's fail. And then we have Delta 94. This was based on more sample sets, so more high gloss, and these were all sprayed over metal panels. They had some textiles. That was originally from the Delta CMC study, and then the elliptical spacing is based on your delta L, your C, and your H. And they're not so independent this time. So here's the equation. So for this, your KL, KC, and KH are all your application factors. And normally these are set at 1. And then your S factors are the only thing that's variable, and they're based on the equation. In this case, your SL is always 1, but then you can see your SC and your SH will change based on your chroma for those two equations. And then the problem with this equation is there is no lightness correction. So everything is based on chroma and hue. So it's important that you remember this if you're looking at colors with the delta E94 equation. So for example, delta E94 compared to CIELAB, this is a non-chromatic color, so we're using L, A, and B, not so much the C and the H. But again, this equation generates the tolerancing based off of C and H. So you can see in the bottom sample that's highlighted in red that we're looking at C and H values, and that's how we're tolerancing things. But it's still a weighted color tolerancing, and it's pretty close between the CIELAB and the delta E94. And the reason for this is that our scaling factors for delta E94 based on the equation are close to 1. And so our delta E star, which is CIELAB, and our delta E94 are both 1 or very close, 1 and 0.99. And that's why this equation has good agreement for non-chromatic colors. When we look at chromatic colors, now our delta E star is 3.06 for our yellow that is more chromatic. And for our yellow that has a hue shift, we're getting a delta E of 2.89. But if I use delta E94 and weighted color tolerancing, now my yellow with my chroma shift is going to be delta E94 of 0.72, because for the delta E94, remember my chroma can shift more than my hue can shift, and so that's okay for this equation. So my CIELAB number is actually too tight for the tolerancing. I need to use delta E94, and that matches more closely to what I see visually for this color. And then my hue change, the yellow H, my hue is different from my standard by minus 2.87. And this gives me an out of spec or minimum of warning of 1.19 for my delta E star 94. So for these two colors, if I use delta E94, it agrees much closer to what I see visual than if I use the standard CIELAB delta E LAB numbers. So this shows you the difference between the CIELAB and the delta E94. So for the CIELAB, all of my points are circles on my scales. So they're always the same size if I don't change any of the variables myself, but they'll generate circles for everywhere I am in color space. And again, back to the original couple slides, when we look at color space, it is not homogeneous. So depending on where I'm in color space, my ellipse size is going to change. So if I look at the CIE94 scale on the right side, everything, the ellipses change and they get longer the farther away I am from the 0 point, because my chroma is increasing as I go away from the 0 point. And remember, my chroma doesn't affect me as much as my hue shift for some colors, but for any chromatic colors, you're going to have more of an elliptical and not a circle for your tolerancing. The next color equation we're going to talk about is delta E2000. And this has some significant improvements over the other equations that we talked about. And this was based a lot on automotive high gloss paint. They did some matte panels too, because they wanted to make sure that it would work in that type of color space also for matte finishes. And the elliptical spacing is based on delta L, delta C, and delta H. It also has a couple corrections that people noticed when they were looking at these newer tile sets. And so one is a rescaling for the A axis, and this is for gray and sometimes some beige colors. And also it has a correction for lightness, chroma, and hue, depending on perception. And then there's a rotational function for blue colors. And I'll talk about those specifically in a second. So for the modification of the A axis, originally, if you look at the bottom left corner, there's a circle. That would be the normal without this modification of the A axis. And on the left side at the bottom, you see the ellipse. So I'm really changing the shape on that axis and making an ellipse and not a circle. So if I look at the differences here, if I use delta E94 for this example, those two samples are a warning. But if I use delta E2000, which matches closer to what I see visually on this gray color, those two samples would be failures. So it's a big deal that this is changing it this much to make you one have a pass and the other one have a fail. And that's why it's super important to pick what color equations you're going to use when you're setting up your color program for all the different colors that you're looking at visually and numerically. There's another portion of the delta E2000 equation that causes a little bit of a difference, and it's called this RT factor. So you see the whole color equation, and then there's plus RT, and then another couple equations. This is the rotational factor, and what this does is it modifies where you are in the blue color space. It gives a tilt to the axis, and that's what we see visually. So this is an important correction that was done for the delta 2000 equation. And here, if you look in the bottom left side, there's a box that has like a blue highlight there. There you can see where it's tilting all the stuff on the blue axis slightly, and that's matching closer to what you see visually. So for example, here we have, if we use delta E94, straight up and down pretty much to back to the center of color space. And there's no rotational factor on this one. And both of these samples are passing. If I use delta E94, it's shifting my axis by 24 degrees based on my calculation and where I am in color space. And this is taking those two passes that I had for delta E94, and both of them would be out of specification. And this would match what you see visually much closer than the delta E94. So again, it's important to think about these things. If you have no blue colors, then I guess you could use delta E94 or delta E2000. But if you have a lot of blue colors, you really want to make sure that you're using the color equation that best represents this. And we have seen this in the industry where we look at some delta E94 colors or 94 measurements versus delta E2000. And the delta E2000 on the blue colors will match more what we see visually. When we see something and we think it should be rejected, the delta E94 could pass and the delta E2000 might fail it. So it's not something that we don't see in the industry. It's definitely there, and it's something you need to be aware of when you're looking at color equations to set up for your color program. So if we look at all these different color systems, so the DIN 99 and the DIN 990 we're not talking about in this particular presentation because those are for metallic colors, and right now we're just talking about solid colors. But if you look at the CIE 94, you see how those ellipses look. The CMC, the ellipses are different. They're in different locations a little bit. And then for the CIE DE 2000, the ellipses are similar, but when you look in the blue range next to that plot, you see how they're tilted for the 2000 equation. So this is kind of a summary for everything. For solid colors, you could use Delta E94 or Delta E2000. Those are the two that we recommend. We do have customers that use CIELAB, and then they do adjust for every single color, depending on where it is in color space and based off of their visually acceptable tolerancing. But again, it's more complicated, and you really have to know what your process is capable of, plus what is going to be visually acceptable for your customer in order to set up these tolerancing. And in Smart Chart, you can also set CIELAB up to have plus or minus, and they can be either uniform, so symmetric differences in your tolerancing, or you could set tolerancing to be more, say, red than green. So you could do 0 to +1 for your A value, or you can make it so it can only be green. So from 0 to -1 for your A value, or the same thing for your L value or your B value. So these are asymmetric tolerancing that you can set up for CIELAB. Delta E94 and Delta E2000, both of these two need to be set up symmetrically. You cannot do asymmetrical tolerancing with those two equations. And then if we're looking at equations that we can use on solid and metallic colors, we would use either the Delta Audi 2000 or Delta combined. And these two equations both account for micas, solid colors, and metallic colors. And they adjust the tolerancing based on the angle, because for solid colors, normally we don't have angles. But for metallic colors, we need to look at the 15 through the 110 to make sure we're covering all our bases on how the color travels. And so the Delta Audi is based on the metallic, which is Delta E DIN 61752, plus Delta E94 for solids, and that gives you the Delta Audi equation. And then for our Delta combined equation, we use the Delta Audi equation for metallic colors and mica colors, and then we use Delta 2000 for the solid colors. And again, the reason we do this is because the Delta 2000 equation has the tilt in the blue section, and also that modification on the A-axis for gray and some tan colors. So that's pretty much the summary. And these equations work in either our Spectra 2 guides or our Spectra 2 profiler, and also in our BICMAC. So both of these equations are available on both. So that is the conclusion. Do we have questions?
That's all, huh, Ray?
That's it.
That's it. Thank you very much. Always educational. And from my marketing perspective, a bit over my head, but this is all good. You teach me something new every time, so I'm getting there. So yeah, we've got a couple questions in here. But actually, let's do the questions, then I'll ask my questions. First one, what lab system is the most accurate? LAB CMC or LAB star?
So for like CIELAB, so the original LAB, if you have non-chromatic colors and you just go with, if my Delta E star is over 1, you're probably going to be okay. But if you have chromatic colors and you're trying to still use an LAB of 1, it's not going to work. You're going to have to individually adjust the L, the A, and the B tolerancing by hand to what you match visually. So back in the beginning, let me see if I can get back there. Give me 1 second.
Sure.
Back here. Here. No, back 1. So this box is what my CIELAB is going to generate for my tolerancing. And again, even in this case where I'm a non-chromatic color, it's pretty good because that circle represents what I say is good visually. So I'm only getting a couple of rejected parts. But if I go to a chromatic color and I use CIELAB tolerancing LAB, now I'm either too small, rejecting good parts, or too big and accepting bad parts. So that's why if you use weighted color tolerancing, it's going to fix these issues for you automatically, and you're not going to have to do it by hand. And that's the benefit of those weighted tolerancing. So to say one's better than the other, it all depends kind of on how you're using it and what you're trying to accomplish. And this is something that anyone who's on the call, if you have questions about anything specific like this, please call us. We'll look at your samples and what you're doing and recommend the best equation for you, because we understand it's not so simple.
Yeah, and that's something I was going to mention too. Just, if you're getting into this or you're at a point where you just need some help or a different someone from the outside to take a look at things, we are always there, always willing to, like Ray said, look at your samples. We have a team that does this. We have technical sales representatives all over the country and world. They can pop in and look at, what your program looks like and offer any recommendations to streamline things. Okay, so go ahead.
No, go ahead. You're fine.
I was just going to go into the next question, but if you have something. Okay. Next question. How does this relate to or affect specular included or specular excluded?
So
that's a good question.
Yeah. So with spins and specs, so normally with the specular included, because it's more the material and not the visual color difference, the tolerancing can be tighter. And for the specs, that's the one that, depending on how chromatic you are, you're going to have to adjust the tolerancing. But it's not affecting spin and specs. It's just the same type of thing. You have to figure out if you want to have it match to what level, right? So I can't tell you that. It depends on, where you are. Like when we talk about 1 for Delta CMC, 1 is based off of automotive specifications. Like I can go into different industries and the tolerance could be like 2, right? Mm-hmm. It just depends on the industry. So it's not necessarily that the spins and specs it's gonna change your tolerancing just because they measure completely differently. 1 includes the gloss and 1 does not. So that's going to be the variation between spins and specs, and your tolerancing may change, but it's not because of the instrument, if that makes sense.
Good. Another question here. I'll just keep reading. Is there a device that can measure color on casted parts?
We need more information.
Yeah. Dave, let me unlock your microphone here. There you go. Now, Dave, if you look in your upper right-hand corner, there's a round circle with a microphone in it. If you click on that, it'll turn green, and then you will be live with us. If you wouldn't mind expounding on your question a little bit. I'll give him a minute here. You might be having some audio problems. If you're not able to unmute yourself, Dave, we can follow up with you directly on that. We'll capture this question. I guess, my overall thought as I was watching the presentation and listening to you, Ray, there's so many variables. How, from the beginning point, where should someone start? Either, look, if they're just new to this, or if they have an existing program that, maybe it's time to take a look at it just to make sure everything's, going as efficient as it can. What are some kind of steps and starting points for them?
So if I was going to go in and try to figure out, I mean, I'm kind of biased because I do all this automotive stuff. So I would go, if it was most automotive plants, I would go directly to Delta Audi or to Delta combined too. I would use one of those equations. But what you need to do is you really, if you're going to do it correctly, you need to have good samples, borderline samples, and bad samples. That's what you say is visually what your idea is for those. And then take those samples, measure them in, and then look at the different color equations and see which one matches closest to your visual perception. And this you can do in Smart Chart. In the lab version, you can take the different, all your measurements, and you can change the equation and adjust them and then see what matches closest to what you see visually. And that's what we do at a lot of the OEMs. When we start working on color programs with them, we have them measure and look at everything visually, and then we make sure that the equation matches what we see visually. And this is kind of why we tell you guys to call us if you want to do this, because it definitely helps for us to look at the data for you too. Because we can give you our idea and we know what to change. If you just start changing, like for Delta CMC, if you just change the L and the C and you don't know what that really means, you could end up with some crazy tolerance that doesn't even make sense.
Yeah.
So that's more why we like to help you in finding those things.
No, that's good.
Definitely you should have samples that are visually acceptable, visually okay, and visually out of tolerance, so that you can figure out what equation to use and what matches best what you need for your parts and your process too, because some people's processes may have a lot of variation, and if we make the tolerance tight, they're never going to make it.
Yeah.
And then everyone just looks at the number and says it fails all the time, and then they think the instrument measures incorrectly or something like that, when it has nothing to do with the instrument itself. It has to do with the color equation that I'm using.
Gotcha. So setting it up so it's in tolerance and also visually acceptable, that's, that's your win-win. Yeah.
Yeah. So, I mean, like we always say, BIC, we measure what you see. And I think that's what we're trying to set up for customers, is to make sure that the visual matches the numeric, so that if the instrument says it's rejected, it should be rejected, and that you're not second guessing the numbers. And to do that, it takes some time, and you really need to know what you're talking about and what you're looking at. But that's my best way to tell people to set them up.
Yeah, no, agree. And like I said, after we stop this presentation, you'll get an automated link with the recording. Grab screenshots of it. If you have questions, if something doesn't make sense next week, just hit reply to any of the marketing messages. I can route them to Ray or the appropriate technical specialist, either in your region or back at our headquarters if we need to run some tests for you or do whatever. But like Ray said, it's just a matter of getting you set up so you're efficient. So it's making sure that the numbers match from the instrument as well as the visual. Because that visual is important. Something on the shelf, that's what is going to affect the consumer.
Yeah.
Are there other, I guess, things that you've seen frequently that customers are doing that isn't quite right? Kind of some frequently,
Yeah. So
issues that you've run into. Yeah.
one thing we see a lot, especially for solids, people always say if it's over 1, it's out of spec. But if I say it's over 1, it's out of spec, now you have to tell me more information. Am I using Delta E star? Am I using Delta E94? Am I using Delta E2000? Because that changes what that 1 means. So a lot of people, I know, like in the past, like people say if your Delta E is over 1, it's out of specification, but it's how that Delta E is defined. So pretend I use a different illuminant, not D65. D65 is the closest to daylight illuminant that we have. But if I have, say, a different illuminant picked, like a illuminant picked, then those answers are different than if I'm using Delta E65, if I'm using an A illuminant. So that's why it's super important if you're talking to other groups in your organization, you really need to know exactly how they're calculating everything, or your number could be totally different than their number. So it's really important. And that's another reason why we kind of lock down Smart Chart for the process version, so that you can't mess with those things. And if you change something, it's only going to show you from this point on. It's not going to change your previous data. Because what was happening was if someone didn't like the answer, they knew they could change the settings for the standard, and then they could get the answer that they want. And this is not what you're supposed to be doing. You're really trying to, you're laughing, but it happens.
I know. I believe it. I believe it. Oh, that's good. Another question in here from Christian. Are these equations available to use with the BIC SpectraGuide Sphere gloss?
So just the SpectraGuide Sphere, the original one?
Yep.
And that, I know, I think you can use CIELAB for sure. You can use, I think, 2094 and CMC. I think those are all available in there. The combined equations for like metallic colors are not available in that instrument because it's only one angle.
Yeah.
And you need multiple angles to measure metallic finishes.
Yes. And Christian, the Spectra guide, we just we're running into some component issues and legacy issues, so we've decided to retire the Spectra guide. We are running a special if anyone's interested in upgrading to the Spectra 2 guide or Spectra 2 Go. I put the link in the chat if anyone's interested. We're offering a 15% discount till the end of the year on that. So just an FYI.
Next question. Perfect time to change to the new one.
Okay, if that's a question, if someone were to upgrade, how would that affect the data, the historical data, or anything moving forward? How would something like that work, right?
So for one thing, the Spectra guide only works with EasyLink. It does not work with Smart Chart. So upgrading to a Spectra 2 guide, I think, is super important because you get all the benefits of Smart Chart with the new instrument.
Yeah.
At the numbers, because we kind of we improved, I guess I should say improved, not modified, improved the Spectra 2 guide for some of the things that we saw in the Spectra guide that they weren't causing problems, but maybe they could be better. So the numbers between the two are going to be slightly different, but the delta should be similar on most colors. For your historical data. But I would recommend measuring good, bad, all that stuff, and verifying your tolerancing if you're getting a new Spectra 2 guide, just to make sure that you're correct.
Yep. Okay, another question here. Thank you for the insightful presentation. Good job, Ray. How do the equations take into account the textures of samples? Could you elaborate on how texture variations influence the calculations?
So the texture doesn't influence the calculation, but the texture influences what you see visually. So it's going to change your numbers. So if, depending on the texture, if I have a flat plaque and then say I measure that, and maybe it's like a matte finish, it's going to be glossier on my flat plaque than it is going to be on my textured surface. So your gloss is going to go down normally on the textured surface. But that has nothing to do with how the instrument measures. That just has to do with the texture changing the gloss level of the material itself. So you would still have to have different tolerancing for the flat panel versus the textured panel because your visual perception of the color is going to be different.
Yeah, yeah, no, that makes sense. Another question here from William. There's a definite need for generally available delta E combined color appearance difference equations published by the CIE and added into the CIE 15 colorimetry publication for the 5th edition. Can BIC please consider moving the entire industrial color field forward by collaborating with the CIE to make this happen?
So currently we have one of our German colleagues is on that board. So I think she's working on that right now. I don't have any updates right at this moment, but I can get them if you would like to, or if you even want to talk to her directly, we could get you in touch with her. And maybe there's some questions that you want to ask that maybe she's not discussing right now, and that would be fine also.
Yeah, we can definitely do that. Is that Sandra?
Yeah, Sandra, yep.
Okay, I will pass along your information there, William. So thank you. Other questions out there? We got maybe time for one more. If anyone has anything out there they need help with, need answered, some clarification.
One other just point for the textures.
Yeah.
The sorry, my computer's decided to update. For the textured surfaces, the Spectre 2 guide and the Spectre guide, both and the Go, all measure with circumferential illumination. So when you're measuring textures, if you're using a directional instrument, you would have to spin it because the texture is going to affect how the measurement comes back on a one directional instrument. On our instruments, you don't have to spin the instrument. You can just measure it the same direction all the time. So just a benefit to our instrument for textured surfaces. And we also have a Spectre 2 profiler that actually measures the texture itself. So that gives you another data point. So you would get color, gloss, and then texture, a 3D, and also a reflectivity measurement. That's pretty cool too. So if anyone needs texture, color, and gloss, please talk to us and we can show you our new instrument, the Spectre 2 Profiler.
Definitely. Yeah, we have reps in all over the place, and they can schedule a demo with you and can do some testing. Excellent. Any final words of wisdom, Ray, before we wrap this up? I know there was a lot of information, so take a look at the recording and take any screenshots of these equations that you need, and definitely reach out. But Ray, any final words?
I mean, my biggest thing is if you're trying to do this, please talk to us because we can make it way less painful for you and give you our insight into what we think the tolerancing should be. And I think we can really help people set up a very good color program for their facilities that will work not just at their facility, but maybe at their sister facilities or at their suppliers or at their OEMs.
Yeah, very good.
That's important.
All right. Well, with that, I think we'll end a couple minutes early here. I'd like to thank everybody who attended. If you have questions or comments or need anything down the road, just hit reply to any of the marketing messages and we'll get it to the appropriate person. Ray, thank you as always. Very informative, educational. You're always teaching me something. So thank you very much for your time and expertise.
Thank you, everybody.
All right. Have a great day, and we look forward to seeing you on future Bit Gardener web seminars. Thank you.
Sounds great. Thanks.